Hello, student. I understand that you missed a day of class and now you are a little behind, but not to fear, I'm here to help you catch up. So the two lessons you missed were lesson 1.4, which is characteristics of polynomial functions, and you missed lesson 1.5, which is graphing polynomial functions using intercepts. So fortunately, these two lessons are connected, so should be easier to learn them more quickly. So anyways, let's get started for lesson 1.4. So characteristics of polynomial functions. So basically, when it's asking for characteristics of a polynomial function, you have to state the sign of the leading coefficient, the degree of the polynomial, the end behavior, the x-intercepts are also known as roots, and then you learn something called order here. And I'll explain what that means after we go over the first few characteristics of the polynomial function. So the way I'm going to do this is I'm just going to show you pure examples. That's the way you're going to learn this in class as well. So given the function y is equal to 2 times x plus 3 times x minus 5 times x minus 7, answer the following. So what's the sign of the leading coefficient? Well, in this situation, the a value is 2, as you can see here. So since 2 is positive, that means the sign of the leading coefficient is a positive. Now, before we go any further, I want to make the note here. Just because if your function is in factored form, just because your a value is a number doesn't mean that's the value of the leading coefficient. Now, in this case, it is 2, but you can't assume that the a value is just the value of the leading coefficient. Sometimes it's not. And the way to do that, it's a little complicated, but I'm not going to be going over that in this lesson because we did not go over it in this lesson. But all you have to know for now is that the sign of the leading coefficient is just positive because the a value is positive. So next up, the degree of the polynomial. So basically, since all the factors are just being multiplied here, you can just add up their exponents. And when you add the exponents up, you get your degree. So 2 is really just 2x to the power of 0. So no exponent there. X plus 3, since there's nothing written there, it's to the power of 1. So the exponent is 1. X minus 5, same thing, to the power of 1. And x minus 7, same thing, to the power of 1. So since these three factors all have an exponent of 1, you just add them all up and you get 3. So the degree of the polynomial is just 3, which makes it an odd degree polynomial. Okay, so now we have end behavior. So if you recall from lesson 1.2, if you know the sign of the leading coefficient and the degree of the polynomial, you know what the end behavior is. And since in this situation, the sign of the leading coefficient is positive and the degree of the polynomial is 3, which means it's an odd degree of polynomial, we know that the end behavior is the polynomial function starts in quadrant 3 and ends in quadrant 1. So we can say starts in quadrant 3 and ends in quadrant 1. All right, so next up we have roots, also known as the x-intercepts. So this is pretty simple here. This is a grade 10 concept, but I'll go over it in case you may have forgotten. So basically, we're just going to set all of our factors here equal to 0 and then just solve for x. So first up, we have x plus 3. So we're going to say x plus 3. We're going to set that to 0. And then when you just solve for x, you get x equals negative 3. So x equals negative 3 is the first root. And next, oh, shoot, that's not equals. X equals negative 3. Let me do this instead. Okay, that's the first root. And I'm not going to show now anymore. You should know what I'm talking about. So if we set x minus 5 equal to 0, if you set x minus 5 equal to 0, you just solve for x. And when you do that, you get x equals 5. So x equals 5. And x minus 7, you just set that equal to 0, and you just solve for x. When you do that, you get x equals 7. So we have x equals 7. So those are your roots, also known as your x-intercepts. Negative 3, 5, and 7. Okay, so now we're going to talk about order. So before we answer the question, what occurs at each root, we need to talk about what order means. So basically, order refers to how many times an x-intercept is repeated. So basically, think of it right now as order is just what the exponent is. Now, I'll go into more detail about what order actually is with a different example. Just it's difficult to do with this example, and you'll see why later. But anyways, we have x plus 3 times x minus 5 times x minus 7. The order of each x-intercept, the order refers to the x-intercept. The order of each x-intercept is just the power or the exponent of what that x-intercept is. So basically, the exponent for x plus 3 is 1, as we said earlier, because there's nothing written there. So the exponent is 1, which means the order is 1. You can think of the exponent as being the order. The same thing for x minus 5. The exponent for x minus 5 is just 1. So the order is 1 for x minus 5, also known as the order is 1 for the x-intercept 5. And same thing for x minus 7. The order for x at 7, x equals 7 is just 1. So we can say here that the order for all x-intercepts is 1. It's just 1. Now, what does this mean? Now, order, basically, it's describing what the behavior of the function is going to be like. So as you know from grade 10, y equals 2 next to the power of 2. This is a quadratic function, which means it's going to have the shape of a parabola. And we have if we have y equals x to the power of 3, this is a cubic function. So it's going to start all the way at the bottom, and it's going to go up, and then at the x-intercept, it's going to go kind of like this. You get the point. It's basically stating the shape of the function. And if you remember from grade 9, you learned about y is equal to x, and this is just a linear function, and x here is just to the power of 1. So therefore, when something is to the power of 1, that means the shape of whatever that thing is going to be linear. So therefore, we can say that when the question asks what occurs at each root, we can say at x equals -3, so at x equals -3, the shape of the function will be linear. And we can actually say this for all of them, because all of them, x equals -3, x equals 7, x equals 7, they all have an order of 1. So we can just say, actually, all x-intercepts in this question have an order of 1, which means the shape of the function at all of these x-intercepts, which means the shape of the function at all these x-intercepts will be linear. We can say that. Now, may seem a little bit confusing, but it's going to make a lot more sense in lesson 1.5. You'll see what I mean. Now, I just want to say something. So let's say you had x minus 7 to the power of 2. How do I do that? To the power of 2. Let's say you had x minus 7 to the power of 2. Since the exponent is 2, that means the order is 2. It's just literally the order you can think of as just being the exponent. And since it's to the power of 2, that means the shape of the function at, in this case, x equals 7, is going to be a parabola, because anything to the power of 2, or in most cases, is a quadratic function. So this also means that, so the way I just explained it, that's the way you can think about it when you're dealing with it and when you're performing calculations with it and graphing. But if you want to stick to the definition as well, let's go back to what order means. It means order refers to how many times an x-intercept is repeated. So basically, here, I'll show you on a whiteboard. So let's say we have a graph here. And let's say we have x minus 3 to the power of 1. Let's just say that. X minus 3, that's just x equals 3. So let's say this is 3 here. And the shape of the function at x equals 3, since the exponent is 1, the order is 1, the shape of the function will be linear at x equals 3. So the function will be like this. It's going to go through 3, kind of like this, kind of like a straight line. And it's only going to go through it once. But now let's say we have a different function. Let's do the same thing, x minus 3, but to the power of 2. This means that at x equals 3, the shape of the function at x equals 3 is going to be quadratic. It's going to be a parabola. Now, in this situation, we're not given enough detail, so we don't know if it's going to look like this or like this. It could be either one of these. Now, in a full equation, you're going to know which one it's supposed to look like, but my point is this is what the shape of the function is going to be like at x equals 3. Now, going back to the definition, it said order is how many times an x-intercept is repeated. Basically, all that means is that you're not going to actually see this, but on Desmos or on a theoretical graph, let's say the shape of the function is like this. You're going to actually have this happen twice, but you're not going to see it because it's going to happen right on top of each other. So, like, for example, at x equals 3, the shape of the function, it's going to look like this. It's going to go through x equals 3, and it's going to be like a parabola, the shape, but it's going to actually happen twice. But you're not going to see it. It's going to look like one because it's just the two lines are right on top of each other. So that's basically what it means when it says order is just how many times the x-intercept is repeated. So yeah, if you are a little bit confused, it should make more sense in the next lesson. But this is basically what order means. Okay, so next up, we have another question. It says determine the equation of a function with zeros at x equals -5, order 1, x equals -2, order 2, x equals 3, order 3. The function passes through the point 2, 5. So first thing I'm going to do is I'm going to say y. Don't know why it keeps doing capital, but well, okay, there we go. We're going to say y. So first of all, let's work backwards for a sec. Let's say we're given this, x minus 5, and we want to figure out the x-intercept. Well, as you know, you just set this to 0 and solve for x. So if we set that to 0 and solve for x, we get x equals 5. Now here, we're trying to create an equation. We're not trying to find the x-intercepts. We already have the x-intercepts. So if we want to create the equation, we have to work backwards. So if it's saying zeros at x equals -5, that means the way it's going to look in the bracket in the equation, it's going to be x plus 5. Because if we have x plus 5, and we want to find the x-intercept, we set that equal to 0, and then we get x equals -5. You get it? So, good. Hopefully you got that, student, whoever the student who missed the class. So yeah, if x is equal to -5, if x is equal to -5, we know that the way it's going to look in the bracket in the equation, it's going to be x plus 5. So x plus 5, that's the way it's going to look. And as you can see here, it says the order is 1, which means that the exponent for x plus 5 is just going to be 1. So we actually don't have to write anything there because if there's no exponent there, it's just to the power of 1. The next x-intercept we have is x equals -2. Now, same concept here. We just have to work backwards. So we know that x plus 2, if that's in a bracket and we set that equal to 0 to find the x-intercept, we get x equals -2. So we know that x equals -2 in this situation is going to be x plus 2. So I'm going to insert an equation here. And you'll see why in a sec. So we're going to say, it's the same thing, x plus 2. Now, notice here how it says the order is 2 for x equals -2, meaning that the exponent for x plus 2 is going to be 2. So we have to put this to the exponent of 2. So that's why I put an equation in there, just to insert the exponent. So now we have x plus 2 to the power of 2. And finally, our final x-intercept, we have x equals 3. The order is 3. So, same thing. We know that x equals 3 as an x-intercept is going to look like x minus 3 in an equation in factored form. So, we'll just put that in there. So, we have x minus 3 and the order is 3. So that means the exponent is 3 for x minus 3. So that's what we're going to do. We're going to put 3 for the exponent. That's it. Now, we have to determine the equation of a function. That means we have to find the a value. And luckily, we're given some good information. It says the function passes through the point 2, 5. So what we can do here is we can plug in x and y for this point here and just solve for a. And then once we do that, we have our equation. So all I'm going to do here is I'm going to say y is equal to, I'm going to say y is equal to a, and then the x point into 5 is 2. So I'm going to say 2 plus 5 times, and then we're going to plug in 2 for x again, and then 2 plus 2, and this is to the power of 2. Actually, I'll make that neater. Sorry. We're going to say 2 plus 2 to the power of 2. And finally, we are going to plug in 2 for this x here, 2 minus 3 to the power of 3. Okay, so we plugged in our x, and our y value is 5. So we're going to plug in 5 for y, and then just the same thing. So, and now we just solve for a. So 5. Actually, I'm going to do this in a calculator. So feel free to get your calculator out as well. So we're going to say 2 plus 5 times 2 plus 2 to the power of 2 times 2 minus 3 to the power of 3. And we get negative 112. So we have 5 is equal to negative 112a. And now we have to solve for a. So what we're going to do here is we're going to divide both sides by negative 112. And when we do that, we get a is equal to five divided by negative 112. This is our a value, 5 over negative 112. Or we can say negative 5 over 112. So the equation for this function is y equals, is there a way I can sort of fraction maybe? Yeah, this way, right? We can say negative 5 over 112. And then we can just put this in here. So that's our equation for the function. Y is equal to negative 100. No, y is equal to negative 5 over 112 times x plus 5 times x plus 2 squared times x minus 3 cubed. All right, now we're on to lesson 1.5. So this is where everything kind of comes together, and this is very related to the previous lesson. So hopefully this one shouldn't be too difficult. So we have graphing polynomial functions using intercepts, x-intercepts. I should change that. X-intercepts. Okay. So here are the steps for graphing polynomial functions. So first of all, you want to find the degree of the polynomial function. You want to find the sign of the leading coefficients. Then you want to find the end behavior of the polynomial function. Then you want to find the y-intercept, and then you want to find the x-intercepts. So as you can see here, a lot of similarities. As you can see, the first 3 steps are just finding characteristics of the function. All right, so now we're going to graph this function, y to x is equal to negative times x plus 3 cubed times x minus 1 squared. Now I already got the information we needed, so I found the degree of the polynomial. So the degree is 5 because we just add up the exponents here, which makes it odd. The sign of the leading coefficient is negative. The end behavior, since the degree is 5, which makes it odd, and since the leading coefficient is negative, we know that the polynomial function starts in quadrant 2 and ends in quadrant 4. I should say ends, sorry, not goes. It ends in quadrant 4. And then to find our x-intercept, our y-intercept, I just plugged in 0 for x. And when you plug in 0 for x, so you plug in 0 for x and you solve, you get negative 27. So the y-intercept is at negative 27. Other than to find the x-intercepts, I just set all my factors equal to 0 in the original equation. So x plus 3, that's just x equals to negative 3. And x minus 1, that's just x equals 1. And the order for x equals negative 3 is 3 because the exponent is 3. And the order for x equals 1 is just 2 because the exponent is 2 for x minus 1. So let's graph this then. Okay, so we have our graph here. This is not going to be to scale. But anyway, so we know that the function, the end behavior, starts in quadrant 2 and ends in quadrant 4. So it's going to start in quadrant 2 and end in quadrant 4. Next thing we can do, doesn't really matter what you do in this order, but I guess I'm going to plot my x-intercepts first. So we have x equals 3 and negative 3. Yeah, we have x equals negative 3. So we can say this is x equals negative 3. And we have x equals 1. Just double checking here on the side. Yep, okay, those are the x-intercepts. And the y-intercept, we can go a little further down, I guess. It is at 0.0, negative 27. Okay, so the function starts in quadrant 2 and ends in quadrant 4. So it goes down, and since the order at x equals negative 3 is, it was 3, we know the shape of the function at x equals negative 3 is going to be cubic, so it's going to look cubic. So we have to make sure it looks cubic. Sorry, I repeated myself too many times there, but just try and emphasize the point. And once it goes through x equals negative 3, we know it has to go through the y-intercept first because that's before the next x-intercept. So it's going to go down, goes through this point here. It's going to go up, and it has to go through this x-intercept. And at x equals 1, the order was 2. So we know that the shape of the function has to be quadratic. So it has to look like this. And that actually has to go through the x-intercept. So that's a bad drawing. But yeah, it has to go through the x-intercept. And this is what your function will kind of look like. Now, note, it could look a little different, but that's okay. As long as you just get a general idea of what the function looks like, that's all you need to do right now. So this is what graphing the function looks like. Okay, so for this one, I thought I'd go through it with you. So we'll do it quickly, don't worry. So the degree, so we're going to just add up the exponents here because they're being multiplied. So 2 plus 3 plus 1, that's just 6. So even degree, sign of leading coefficient. The sign of leading coefficient. So since the a value is just 1, it's positive. Sign of the end behavior. Okay, so since the sign of the leading coefficient is positive, and since the degree is even, the end behavior. So the polynomial function starts in quadrant 2 and ends in quadrant 1. So that's the end behavior. The y-intercept, that's going to be, so we're basically going to plug in 0 for x, and we're just going to solve. So I'm going to do that on my calculator. So this is the y-intercept, 0.0 negative 5,400. And for our x-intercepts, we are just going to solve or set them equal to 0. Okay, so x minus 5, that's just x equals 5. Sorry, x equals 5. X minus 3, that's just x equals 3. And x plus 8, that's just x equals negative 8. The order for x equals 5, its order is 2 because the exponent is 2 for x minus 5. The order for x equals 3 is 3 because the exponent is 3 for x minus 3. And the order for x equals negative 8 is just 1 because the exponent is 1 for x plus 8. Okay, so now that we have all our information, we can graph now. Okay, so the first thing I'm going to do, end behavior. So the end behavior starts in quadrant 2, ends in quadrant 1. So it's going to start in quadrant 2, end in quadrant 1. Next thing I'm going to do is I'm going to plot my y-intercept. So that's at point negative, that's at point 0, negative 5,400. Sorry, I can't even say words anymore. It's not easy to write with this either. Should have done something else, but anyways. Okay, so this is our y-intercept, and I'm going to plot my x-intercept. So we have x equals 5, so I'm going to put that over here. We have what? We have x equals 3. So I'm going to put that over here. And we have x equals 8, negative 8. X equals negative 8, so I'm going to put that here. All right, so we're going to start in quadrant 2. The order at x equals negative 8 is just 1. So the function is just going to go through 8 pretty straight. It's going to be linear. It's going to go through your y-intercept. It's going to go back up because it has to go through x equals 3. And at x equals 3, the order is 3, which means the shape of the function is going to be cubic. So the shape of the function is going to be cubic. And then it has to go through x equals 5. And at x equals 5, the shape of the function is quadratic because the order is 2. So it's going to go down and it's going to look like a quadratic. And it's going to look like that. So it finishes in quadrant 1 like that, but it started in quadrant 2. So it goes like that. All right, now I do want to say, if in case you don't know whether the function is supposed to go through a point or not go through a point, basically everything I said before holds true. So basically, if your, let's say your order is 1, that means the shape of the function is going to be linear. Let's say your order is 2, that means the shape of the function is going to be a quadratic. And let's say the order is 3, that means the shape of the function is going to be cubic. But just a general rule of thumb, if the order is odd, that means it's going to go through the x-intercept, or the x-axis. So as you can see here, the order is 1 at x equals negative 8. So it went through the x-intercept at where the shape was linear. But at x equals 5, for example, since the order is 2, it still had a shape of a quadratic, but it didn't go through the through the x-axis. So if the order is even, if it's an even number, it won't go through the x-axis, but if it's odd, it will go through the x-axis. So yeah. Okay, so last thing we have to go over what absolute maximum and minimum values are. So basically, I'm going to read the definitions to you, but these definitions are a little bit confusing. So after I read them to you, I'm just going to show you some examples. So anyways, a function f has an absolute maximum at a if f at a is greater than or equal to f at x for all values of x. And a function f has an absolute minimum at a if f at a is less than or equal to f at x for all values of x. So that's a pretty complicated definition, but I'll show you what it means after I read the other definitions. So for local maximum and minimum values, a function f has a local max or relative maximum. Local and relative mean the same thing. They have this, or relative maximum at a if f at a is greater than or equal to f at x when x is very close to a, and if function f has a local minimum or relative minimum at a if f at a is less than or equal to f at x when x is very close to a. And here are some important notes. So when maximum or minimum is used without clarifying whether a point is an absolute or local value, it is assumed that the point is an absolute maximum or minimum. Also, odd degree polynomials do not have absolute maximum or minimum points. So let's go to the whiteboard. Okay, so with this example, first of all, since the function starts in quadrant 3 over here and ends in quadrant 4, we know that it's even degree. So as I read earlier, if the function is odd degree, it's not going to have an absolute max or minimum value because the function just goes down and up forever. But here it doesn't. So basically the absolute maximum, you can just think of it as what's the highest point? What's the highest point? And in this situation, this is our highest point. This is the highest point on the graph. Anything to the left of it is lower, and anything to the right of it is lower. So this point is the absolute maximum. Now, what about the absolute minimum? Well, in this situation, it doesn't, because the graph just goes down forever, as you can see indicated by the arrows. It just goes down forever. When it goes down forever, it doesn't have an absolute minimum. And the same applies if it were the opposite. If the graph were pointing up, so for example, say we had this. Let's say we had a graph like this. Well, in this situation, this would be the absolute minimum because it's the lowest point on the graph. Anything to the left of it is greater and anything to the right of it is greater. And the absolute maximum, sorry, if I said absolute maximum, I meant absolute minimum for this point. This is the absolute minimum. And for the absolute maximum, there is no absolute maximum because the graph just goes up forever. All right, so what about the local max or min? Well, you could really try to understand the definition, and I'm sure many of you can. And I'm sure you can. But if you want to try to simplify it, in this situation, the relative maximum, you're kind of just going to look for the second highest point on this graph. And it's the same thing if you were looking for the relative minimum. You would look for the second lowest point on the graph. But in this situation, we're looking for a local or relative maximum point. So that's like the second highest point. So in this situation, it would be this point over here. Because anything to the left of it, it's lower, and anything to the right of it, or anything to the left around that point is lower than it, and anything to the right around that point is lower than it. And it's the second highest point on the graph. So this is the relative or local maximum. So yeah, that's basically what absolute maximum minimums and relative or local maximum minimums are. All right, so that's it for lesson 1.4 and lesson 1.5. I apologize for the lengthy video, and I apologize for taking a little bit of time when calculating things, but I hope this was informative.